there. In this video, we're going to consider another style of solids of revolution that are obtained by revolving them around the y-axis instead of the x-axis. Some people will refer to these types of problems as disk method problems, but I will not necessarily be focusing in on that particular type of solution. So let us consider the following curve. So we're going to be looking at the function f of x is equal to x to the 2/3. So as we may already know, this looks like pretty much a bird graph, right? So that's going to be that curve. And let's assume the line y is equal to 8. So y is equal to 8 is going to be somewhere up here. And let's consider this region here. So call that A. So what we're going to do is we're going to revolve the area A about the y-axis. So what is that going to look like? So that means we're going to have a bunch of circles sort of circling around the y-axis. So the question then becomes, what is the area, or what is the volume or surface area of the solid obtained? Okay, great. So I'm going to look at this from a different perspective in terms of the solution. So I'm going to be looking at this graph. So this is x, and this is y. And this is our curve. So this is y is equal to x to the 2/3. So I'm going to be referencing a similar function, or a similar relation rather. Let this be y and let this be x, or vice versa. So I'm going to be considering this curve, this relation. So this relation is x is equal to y to the 2/3. So all I've done is reversed the x and y axes. So one should be able to at least agree that if we revolve this original curve around the y-axis, that will be the same exact solid as if we were to revolve this curve about the x-axis. And we already know how to deal with these types of solids, so we're going to be solving this one, which is equivalent to the original. So we need to write this in terms of some function of x. Now remember, this relation is not a function of x, so we need to only focus on the top or bottom part. Depends which one you're more comfortable with. Alright, so if I solve this equation for y, what can I do? So I can cube both sides of this equation. So that means x cubed is going to be equal to y squared. And then I can take the square root of both sides of this equation. So I get that the absolute value of y is going to be equal to x to the 3/2, which means that y is either equal to the positive version or y is equal to the negative version. So we will be focusing on the top piece. So the top piece, so x to the 3/2, that is going to be this curve. So this is y is equal to x to the 3/2, and its mirror image is down there. So we're going to be revolving this curve around the x-axis. So if we originally had y is equal to 8, this is equivalent to going up to x is equal to 8. So we're going to do this the same exact way as before. So the volume is going to be equal to the sum from 0 to 8. So exactly what is that value? So when x is equal to 8, what do we have? So the integral from 0 to 8 of x to the 3/2. So we're going to be summing up a bunch of circle areas. So that's going to be pi r squared dx. Alright, so if that is the case, then that means our volume is given by the integral pi times the integral from 0 to 8 of x cubed dx, which is just equal to pi times the antiderivative of x to the 3rd, which is going to be 1/4, x to the 4th, evaluated to x equals 8, and x equals 0. So of course that's going to be equal to, so once we have that, that's going to be equal to 8 to the 4th pi divided by 4. And one can verify that that's going to be equal to 1024 pi, and that's going to be cubic units. And similarly, you can find the surface area by integrating the circumferences. So then I go from 0 to 8 of 2 pi r dx. And you can find that integral out if you wish as an exercise for you. So let's do a more involved example. So example 2. So I'm going to consider the following. So I'm going to consider two curves. I'm going to be looking at y is equal to x squared. And I'm going to be looking at this curve, y is equal to x. And I'm going to be focusing on this area here. So I'm going to look at their mirror images. So there's the red area there. So there's going to be some points of intersection there. I'll draw a little line there. So if I revolve this around the vertical axis, I'm going to get a solid whose interior is missing. So if we sort of look at its side image, so what do we have? So we're going to have a line that goes up, a parabola that goes over, or a radical function rather, and we're going to be focusing in on this area here. So we can look at its mirror images. So blue line, upside down side parabola, red region. We're going to be revolving this around the x-axis. So we're going to be looking for that green area, and as before, we're going to be taking away this yellow area that's on the interior of this. So it's, again, like a cup or a cone with a slightly smooth edge on that. All right, so what are these curves of interest? So if this curve is equal to y squared, it's very easy to show that this top function is going to be y is equal to the square root of x, and the bottom is y is equal to negative square root of x. It's very easy to see if that's y is equal to x. This is also y is equal to x. It's its own function since it's the axis of symmetry, and its mirror image is y is equal to negative x. All right, so how can we find the volume of that solid of revolution? So it's going to be the volume of the exterior minus the volume of the interior, because we're taking the whole region, which is generated by revolving y is equal to the square root of x, and taking away that interior cone that's drawn in yellow. So when is x squared equal to x? Or in detail, when is x equal to the square root of x? So we can solve this equation and square both sides. So that means x squared must be equal to x, which means that x squared minus x must be equal to 0. So x times x minus 1 must be equal to 0. So x is equal to 0 and x is equal to 1. So we have x equals 0 here, x is equal to 1 here, and that gives us our bound for our integral. So the volume is going to be equal to the integral from 0 to 1 of pi r squared. So pi r squared. So the exterior function is going to be the square root of x. So pi r is given by square root of x squared dx minus the interior volume, which is going to be the integral from 0 to 1 of pi r squared. And r in this case is going to be the function x. So pi r squared is just a bunch of areas. So let's simplify this. So the volume is going to be equal to pi times the integral from 0 to 1 of x dx minus pi times the integral from 0 to 1 of x squared dx. So therefore the volume is going to be equal to pi times, so the antiderivative of x is going to be 1/2 x squared. The antiderivative of x squared is going to be 1/3 x cubed. And we're going to evaluate this from 1 to 0. 0 goes to 0, so that's no issue. So we just plug in 1. So the volume is going to be equal to pi times 1/2 minus 1/3. We can get a common denominator here, multiply by 3, multiply by 2. So we have 3 minus 2 over 6. So that means the volume is going to be equal to pi times, so 3 minus 2 is 1 over 6, or just pi over 6. And since this is a volume, this is going to be cubic units. Similarly, you can find the surface area as we did in the previous video, but this is a method in finding volumes and surface areas as revolutions if you're revolving things around the y-axis. So instead of looking at this, since we're usually more comfortable with integrating with respect to x, we instead look at its affine transformation and find its volume and surface area, since they are pretty much the same object, just sort of translated in spatial space.